Welcome back to this lecture series on deep learning. In this lecture, we'll discuss gradient-based optimization in deep learning. Why we should learn gradient-based optimization? Because it is a core technique that powers learning in deep neural networks. Without it, models would not know how to adjust their internal parameters to minimize errors and improve performance. Gradient-based methods allow networks to learn from data by systematically reducing the loss function through calculated updates. Whether training is a simple regression model or a massive transformer like GPT, gradient based optimization enables the model to adopt, generalize, and make accurate predictions, making it essential for anyone working in machine learning or deep learning. We'll see one by one. First, introduction to gradient based optimization. The gradient descent is the foundation of optimization technique. Optimization in deep learning, enabling the neural network to learn by minimizing the loss function, which represents how wrong the model's predictions are compared to actual outcomes. During training, deep learning models perform a forward pass and a backward pass to make predictions and a backward pass of loss functions with respect to each parameters. These gradients indicate how to change weights to reduce the loss functions. We'll see the equation. The basic update rule, the general update rule is given by theta is equal to theta minus eta into del theta of L theta. Here, the theta represents the weight of the model. Weight of the model. Eta. This eta represents the learning rate. What do you mean by learning rate? Which controls how big each update step is. And del theta, this del of theta, this is a gradient of loss function with respect to the weight value. In the deep learning model, this rule is applied to every weight in each layer. Thus, gradient descent allows a deep network to gradually correct its internal parameters and improve predictions accuracy over multiple iterations. So this is what I've said. Backward passes and forward passes in the every layer will be there. These updates are led to reduce the training loss. Next, batch gradient descent. In the batch gradient descent, calculate the gradient loss function using the entire training set. Instead of taking one or two, it will be taking entire training data set before updating the model parameters. The update equation is given by eta, same thing, eta into theta minus eta into del theta into L theta. This method provides a highly accurate gradient since it uses the all data, but it becomes computationally expensive because it's slow when data sets are because data sets are very large. Entire data we are going to take, so it is a computationally expensive and it is very slow processing, but it requires storing the whole data set in the memory. This is also one drawback, which is often impractical. In deep learning, batch gradient descent is applied during back propagation, updating every weight in the model after evaluating the entire data set. It is best suited for a small data set and a simpler model, such as disease detection, using the limited clinical data. Next, stochastic gradient descent. SGD represents stochastic gradient descent. Stochastic gradient descent updates the model parameter using a single training set. Only one training example it will be taking at each iteration. This equation is given by theta into eta, del theta, L of theta, xi, yi. Here xi and yi represents the only one input and only one input output pair. It is used to compute the gradient. This makes the training process fast and efficient, especially for large data sets, but also introduces the noisy updates. This is here the noisy update. That is one drawback. which can make the convergence path unstable. In deep learning, this means what it will do is in the deep learning, so noisy updates it will be giving, which can make the convergence path unstable. In deep learning, this means every layer weights are updated frequently, even before seeing the full data set, which helps the model adopt quickly. It is widely used in the real time processing applications like live recommendation systems, where models must update rapidly as new user data arrives. Next, mini batch gradient descent. Mini batch gradient descent blends the benefits of batch and stochastic methods. Instead of using entire data set or a single example, as we have seen before, it uses the small group of samples, say for example 32 or 64 at each step. The update rule is given by theta in theta 1 by m summation of 1 to m del theta into L of theta xi yi. And here this equation means the gradient is averaged over a small mini batch of m samples. In deep learning, this is the most commonly used technique. Each mini batch flows through the network, computes gradients layer by layer, and updates parameters efficiently. It strikes a good balance between computation time and accuracy. It is especially uh, uh, it is especially useful in training convolution neural networks for image classification and object detection, where large data sets like CIFAR or image nets are processed. Here in this case, CIFAR or image nets are used data sets. These are all the available data sets are used for this processed or processed in parts. Next, stochastic gradient with the momentum. Stochastic gradient with the momentum enhances the basic stochastic gradient by incorporating a velocity term that carries forward some of the fast update directions. The equation is given by Vt is equal to gamma into Vt minus 1 eta and del theta L of theta. Theta is equal to theta minus Vt. And here the in this equation, the Vt is this Vt represents the velocity. Vt represents the velocity, and gamma is the momentum of the gradient. Momentum of the gradient, the momentum coefficient. The value of the gamma is about 0.9. This technique helps smooth out oscillations during training, especially in areas where the gradient changes direction rapidly, such as steep valleys or ravines. In deep learning, this method ensures that updates are more stable and converge faster, particularly in very deep networks like VGG or RESTnet. It is widely used in object detection models like YOLO, and where deep networks benefit from the stable directional learning. Next, RMS prop. This RMS prop means root mean square propagation. Root mean square propagation. It modifies the learning rate of each parameter for each parameter individually by maintaining a running average of the squared gradient. See here, squared gradient, beta into Vt minus 1, 1 minus beta, squared gradient. This data is given by this formula. And here Vt accumulates the history of the squared gradient and dividing by Vt here. This Vt into that is eta epsilon scales up to update the size. This approach prevents exploiting or vanishing gradient by dynamically adjusting a step size. In deep learning, RMS propagation is especially effective in recurrent neural networks. RNN means recurrent neural networks, which process sequential data like time series or text. It stabilizes the training process in models where gradients can change rapidly across time steps. And the common use cases of this type is include a stock price prediction, weather forecasting, and language modeling. Next, Adam optimizer. Adam means adoptive. This Adam represents adoptive, adoptive moment estimation. Estimation. Adam means adaptive moment estimation. It combines the advantage of momentum and RMSprop by computing both the first moment means mean and the second moment variance of the gradient. The equations are given by the first equation mt into beta 1 mt minus 1 plus 1 minus beta 1 theta L theta. Here the second momentum is given by Vt B2 Vt minus 1 beta 2 and it is square. Next the bias convergence is given by mt cap of mt divided by 1 minus beta 1 transpose, that is T. Vt caps equal to 1 minus Vt divided by, this is the formula. Next parameter update is given by theta is equal to this value. We are going to one by one, we are going to substitute and we are going to get the value. For this, we are going to substitute in this, and here we are going to substitute in, we are going to make use of this. The Adam automatically adjusts the learning rate for each weight and includes momentum to stabilize updates. In deep learning, Adam is the default optimizer for training large-scale complex models such as transformers. It would it works well on unstructured data. Means what are all the unstructured data we are using it. So this unstructured data like text, audio, and images and enables a rapid convergence. It is used in BERT, GPT, and many NLP applications like chatbots, question answering, and machine translation. These are all the applications of Adam Optimizer. Coming into the summary table, and the optimizer is batch equation summary, deep learning link and application example. To summarize the gradient based optimization, it provides the engine for learning deep neural networks. Batch gradient descent is accurate but slow, best for small data. Next one is SGD is fast and supports online learning but can be noisy. Mini batch gradient descent is most widely used, offering balance of speed and stability. Stochastic gradient with momentum improves convergence by using fast gradient to accelerate progress. And RMS probe is ideal for sequential models like RNN, adopting the learning rate to prevent oscillations. Next, the final one is finally Adam stands out for its adaptive capabilities and is preferred in training deep, large scale model such as language and vision transformers. Each optimizer has a specific role depending on the data type, model architecture, and training environment. Hope everyone understood the equations and the optimization techniques. Coming into the conclusion, gradient based optimization is foundation for how deep learning models learn and improve. It guides the adjustments of weights in neural networks through calculated steps and minimize prediction error. By understanding and applying various gradient based methods, we can train models more effectively, ensuring faster convergence and better accuracy. Mastery of this concept is essential for developing intelligent systems that can adopt and perform well in real world tasks. This is the main advantage of using the stochastic methods. Hope everyone understood the concepts of this gradient optimization techniques. The remaining things we'll discuss in the next lecture. Thank you.